Hi guys. Here we are. We're back at my kitchen table to discuss chapter 7. So you may be wondering what happened to chapter 6. It is actually like the chemistry of life science, which we will cover next year when you guys take biology. It's kind of the same material, so I'm going to keep it till next year for us, just to kind of so we don't have to repeat it, but also to kind of save time because there's certain things I want to get through, and so we're going to come back to that one. But anyway, we're on to chapter 7, which is chemical reactions. And in a chemical reaction, you have a process that occurs where you take a substance and you change it into one or more different substances. That's kind of the definition of it. And the big things that occur, not visibly necessarily, but chemically, molecularly, are that the chemical bonds are broken and the atoms are rearranged. And that doesn't sound like that big a deal. Remember, we're talking about atom, which is super duper tiny, but that change can have very significant, some very significant effects on the overall substance. Okay, so for us, we don't see the molecules switch places. We don't see the bonds break, but we do possibly see some visible evidence. And so I have a list here. This is the list that your book has, and I actually left a couple off, I think, because they kind of were repetitive to me. But if you mix two liquids and you see a solid formed, that is evidence of a chemical change. You have a new substance. That solid is a new substance. And this word right here, this precipitate, that word is a fancy word for solid. And so if you see a precipitate formed, you know that a chemical change has happened. If you see bubbles, and this is not bubbles from like boiling the liquid. This is, I put two liquids together and they start to bubble, or a liquid and a solid. So if you guys ever made, like the classic volcano where you take vinegar and baking soda and it bubbles, that is a chemical change. Also, if energy is released, so typically, energy, again, we can't really see it, but if we see light, if we feel heat, if sometimes we hear a sound, then we know that energy has been released, and that is a chemical change. If you smell a new odor, this one is, like if you've ever smelled rotting food. When food rots, one of the kind of the byproducts really is this odor, and so that's an indication something new is there. And then let's see, a temperature change. So this is a temperature change from inside. This isn't me like putting it in the oven or me putting it, over a Bunsen burner. This is me again combining two things and then like the beaker getting warm. Like the little hot hands packs that you guys have, now that it's getting colder, that is a chemical change. And then finally, if you get a new color. So if I mix two things together and I have a brand new color, I mix two clear liquids and they turn, yellow or something like that, that is a chemical change. Hopefully we'll find a lab where we can see some of these things so you guys can see them in person. Okay, so now writing chemical equations. We practiced in chapter 5 on writing compounds, and this is just kind of a continuation of that, but adding a little bit to make it more of kind of like a chemical sentence. So when you write chemical equations, you have a combination of chemical formulas, which we've practiced, and then other symbols that model a chemical reaction. And it's basically just a shorthand way to describe what's going on. You'll see some different numbers. I have them labeled there on that equation. You will use coefficients that are going to be there to balance the equation. And that word balance just means to make everything equal on both sides. And then when you write your elements and your compounds, they are written with the necessary subscripts, either from prefixes, if you're talking about a covalent compound, or from balancing out the ionic charges if you're dealing with an ionic compound. And so that's the way that those kind of work. We're going to do some practice on these in in some of the following slides. So I may not fill anything out necessarily as we go through this video, but in class we'll go through and do some practice. Okay, so with this balancing, equations are balanced because they follow the law of conservation of matter, which we've talked about the law of conservation of energy a little bit. Same thing applies to matter. Matter can't be created or destroyed, it only changes forms. So in chemical reactions, what that means is that the atoms are rearranged, but you'll always have the same number of atoms that you started with. So what is on one side of the arrow is equal to what is on the other side of the arrow. And so when you balance, you're going to use coefficients that can be added to the equation in front of different compounds to balance or to make both sides equal. Okay, so there are some equations here for us to practice balancing. I'm going to do number one, but we will do the others together in class, and then I'll have some other practice for you. Okay, so my first recommendation to you if you're balancing reactions is to use a pencil, because it sometimes takes some back and forth. But other than that, it's just kind of back and forth. I always kind of tell people, you might want to start by thinking of this arrow as an equal sign. So it is an equal sign. So it's on one side equals what's on the other. So start with the first element. I have one zinc here. So here's one zinc. Over here, I have one zinc. So 1 equals 1. So I'm already good with the zinc. So then I go to the oxygen. So notice in the oxygen, I have 2 here. Remember, it's a Brinkelhoff. So if it's by itself, there has to be 2. And then in this compound, this zinc oxide, I only have 1. That's because that compound is balanced the way that it is written, so it's all good. But my O's aren't balanced. I have 2 on one side and 1 on the other. The only thing that I can do to balance is add a coefficient. And I can't add a coefficient anywhere except where I have written blanks or in front of each of the compounds. So I put a 2 here. So that makes my O's good. But now look what I've done. I've changed my zincs. So now I have 2 zincs and 1 zinc. So now, in order to balance my zincs, I come back over here and put a 2. So now if I check, I have zinc, and there are 2 of them per side, and oxygen, and there are 2 of them per side. So it is all good. That blank in the middle or the blank in front of the oxygen, you can leave it. Excuse me, my nose is really itchy. You can leave it, or you could put a 1. I like to always put the 1s just because that way I know I've looked at all of the elements and everything's good. Okay, so we'll do the rest of those in class. I would encourage you to maybe try them on your own and just see how you do. Oh, I see a typo, by the way. That is I2 right there. Okay, so anyway, so try those, and then we will do them in class together. Okay, so now what if you need to write the equation? What if you are given like the words, but you need to write it in that shorthand form? There are, good grief, there are 3 basic steps to doing that. And so first you want to write the correct formula for each reactant and each product. So remember, if it's a diatomic element, one of the Brinkelhoffs, that's automatically, 2 something. So if I said oxygen reacts with, for oxygen, you would put O2. Then for other compounds, make sure that your subscripts are correct, that your oxidation numbers will equal 0. And for covalent compounds, your little subscripts are given by prefixes. Then you have some other symbols. You have an arrow, which means yields or produces or forms. You have a plus sign, which is and or combines with, reacts with. And then sometimes you'll see an arrow with this little triangle over it. That little triangle is like a heat. It's like a little flame. And so if it says something about when heated, oxygen does this or that, that's what that little symbol is. And then your last step typically is to balance the reaction. Now I have some more practice ones of these. And so we'll do these together in class and kind of go and practice naming on that also. Okay, so here's that practice. We're actually going to do all these together in class, but I would encourage you to try them if you have a chance. Okay, so now working with these chemical equations. So what's the point of balancing equations? What's the deal with that? So here's the deal. A balanced equation shows, or an equation shows what's happening in terms of molecules or atoms. This is starting, this is rearranging, so I'm getting this new product. In an actual lab, most chemists are working with really large amounts of chemicals to make new compounds. So if they're making some kind of new medication, they're recombining things to see what they can get. And so if they're working with, measurable or large amounts of chemicals, that means they are working with absolutely enormous amounts of molecules and atoms, because remember, they are, microscopic. And so chemists typically use a conversion, and this conversion is the mole. And you guys have seen the moles up in my room. I'll have some mole cartoons out here pretty quick, but it is a conversion unit. It's kind of like saying 12 is equal to 1 dozen of something. But for a mole, 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules or ions. And so, which of course it's way easier to multiply by 1 than by 6.02 times 10 to the 23rd, because that's a big, huge number there. So if I'm balancing an equation, I'm showing the ratio of molecules to atoms, and that makes the work, the math, much easier and much quicker to do because of just the ease of the calculations instead of dealing with ginormous numbers. And so that's really the reason, that's the purpose for balancing, is to show what that ratio is. Okay, so now on to the types of chemical reactions. So there are different kinds. We're going to talk about several of the different kinds. I've got some pictures to hopefully kind of show you what that looks like. But starting out, we're going to start with a synthesis reaction. Synthesis, that word typically means to make something. And so in a synthesis reaction, you combine 2 or more elements into one large product. So my little blue circles there, I have A plus B produces AB. So 2 things combine to form one thing. That's synthesis. So anytime you see something that looks similar to that, that is a synthesis reaction. Decomposition is the opposite. So I have a single large reactant and it breaks into 2 or more smaller products. So now my AB is together, and then when it splits, I have A and B separate. That is decomposition, so breaking down of something. Okay, then we have single replacement. So now I have a compound, so that's AB, and it is reacting with a single element, so that's C. In a single reaction equation, 2 elements basically swap places. So one element in a compound is replaced by another single element. So in this case, the C switches places with the A. The C switches places. Good grief, Kimberly. The C switches places. Can I not erase on here? With, I hit the right button. Oh my gosh, one of those old people, aren't I? Okay, there. So now the C, okay, I said it right. My word. The C switches places with the A. And so they trade. And so now the B and the C are together and A is single. Yikes, that was painful. Okay, and then double replacement reaction. 2 compounds switch the cations or the metals, the first element, or they switch the second elements. And so, so in this case, I'm going to say that A and B swap places. So now I end up with the B with the X and the A with the Y. And so you just have this double replacement reaction, and you get 2 new compounds. Okay, and then the last one, and again, these can all probably be rearranged into multiple categories, but these are kind of the main 5. You have a combustion reaction, and this is typically when a fuel, which is a carbon and hydrogen compound, reacts with oxygen. Combustion reactions are really easy to recognize because they always produce the same products. The 2 chemical products are water and carbon dioxide. You'll also get light and heat. I mean, you know, it's combustion, so there's going to be more than that. But in terms of chemicals, those are going to be the two compounds that are produced. Okay, so now energy in these reactions. So is there always energy involved? Well, you know, kind of what's happening with the reaction. So remember, reactions happen and they start with energy being used to break the bonds. So you have to separate the elements. And then when the bonds reform, energy is released. The total amount of energy used and released determines if overall the reaction gives off or absorbs energy. And so you've probably heard these terms, exothermic and endothermic. Exothermic overall, they are reactions that release energy as heat. Okay, so these are the hot hands things. When heat is given off, you physically feel heat. Endothermic reactions are reactions that have to absorb more energy than they release. There are some things when you mix them together, they actually feel colder. But it also could be things like, you know, if I have to heat something up to get it to happen, that's typically considered endothermic. Okay, so now these graphs, I know there's kind of a lot going on there, but they show kind of what is happening energy-wise. So energy is over here on the y-axis, and the bottom is just kind of like a time. So you start here with the reactants. So in exothermic, I start my reactants at a fairly high energy level, and by the time I get to my products, it's lower, which means that energy has been released. Like somehow those levels have changed because energy has been released. Endothermic is just the opposite. I start at a pretty low amount of energy with my reactants, and I end at a pretty high amount for products. So at some point, energy went into that to raise that energy level. Notice that there's kind of this big bump in the middle of both of these reactions. That is a representation of the activation energy. And most reactions have some measurable activation energy, which means they have to kind of get to a point before the reaction actually goes. And so, so you have to build up some energy in order for the reaction to happen. That's the activation energy. And we'll talk way more about that in chemistry. We'll also talk about it next year when we do our chemistry chapter for life science things, because it's a big deal in terms of a lot of the enzymes in your body and how they work. They help with kind of overcoming some of this energy. Okay, so now conservation of energy. Energy follows the law of conservation of energy. It's not created or destroyed, it only changes form. So it sounds just like what we talked about with matter. And so here's some typical energy transformations, what I have listed on there. That first one is, you know, a person eats something, that's chemical energy. They can transform that into mechanical energy by motion, moving in some way. Radiant energy, sunlight, can be transformed by plants into chemical energy. That's glucose, the carbohydrates that plants put together. Another chemical energy in motion, this is your car. The chemical energy in that case is gasoline. And then you guys are all familiar with electricity, electrical energy. We use it to do all kinds of things. This example shows you it's transferring it to thermal energy. So now, moving on, and we're kind of flying through this like we usually do on these videos. The last section of chapter 7 is about reaction rates and equilibrium. So kind of why are reactions different? And so one thing to know is that the reactants, or the starting points of a reaction, have to come in contact with each other. And this is modeled on the collision model. So they actually have to collide, and they have to collide with enough energy to react. And then the rate of the reaction depends on how quickly the reactions occur, and like I said, if there's enough energy to start the reaction. So molecules have to hit pretty hard in order for anything to come out of that reaction. And so that's the collision model. And then, how often they hit and how often they have enough energy determines the reaction rate. And so there are several things that can determine the reaction rate. Surface area. So surface area basically means there's more reactants that are exposed to be able to react. And so I stuck an example on this one because basically the smaller the parts, the easier it will dissolve. So you can think of that like, so powdered sugar is going to dissolve much more quickly than a sugar cube. Okay, just because it has higher surface area. I can get to all sides of a single, little powder or a little piece of sugar, but on a cube I can only get to the 4 sides, and so the pieces in the middle takes me longer to get there because you have to go through everything on the outside. Stirring. So if I'm, physically moving the reactants around, it gives them a higher chance of contacting each other, of that collision. And then also if you're moving them faster, then they have more energy built up. Temperature goes to motion in terms of the molecules. They're moving faster when they're warmer, so they're going to have a higher chance of contacting each other, more movement, but again, enough energy, enough speed when they actually come in contact to react. Concentration is real similar to surface area. So if I have more molecules in the space, more chances for them to collide, to contact, then it's going to react faster. And so, we'll talk about some different examples. And then the last one is a catalyst. A catalyst is a substance that lowers the activation energy. So that hill that we talked about on the previous the slide a couple slides ago, if I can lower that hill somehow, basically create a shortcut, then I am increasing the possibility that a reaction or a collision will happen, that I'll have a reaction. And so catalysts are something you use all the time. Your body uses them all the time, but we'll talk about some other examples of those. Okay, then finally, just real quick, I go over this a lot more detail when you guys take chemistry, but there are lots of reactions, many of them that are reversible, which means they proceed forward, like, left to right, and also backwards, right to left. You can recognize a reversible reaction by a 2-headed arrow, by a double arrow, and they're, like I said, they're super common. It doesn't affect balancing, you don't do anything different there. You just know that it goes forward and backwards. Typically, with reversible reactions, they can reach equilibrium if the two reactions, the forward and the backward, are happening at the same rate. It doesn't mean that I have equal amounts necessarily on either side of the arrow. Balancing, yes, I would, but it doesn't mean necessarily, weight-wise they're the same, but those reactions are happening at the same rate. But the thing with equilibrium is that visibly nothing's really changing. Like in your water bottle, that's sitting probably somewhere close to you, you have H2O, but it is just as rapidly breaking down into H and O, H2 and O2. But because it is happening so fast, the reaction is going forward and backward. We don't see it. They don't explode because, remember how unstable those two things are? It's so rapid and so quick that they basically just sit there like a cup of water. So now, equilibrium can be disturbed. And so if I change concentrations, if I heat it up, if I add a catalyst, well, actually catalyst won't affect it, but if I change the pressure, if we're talking about gases, I can disrupt equilibrium and the reaction will adjust itself to get back to that equilibrium. And the process, and this is the last little section in your book, this process of returning to equilibrium is described by a principle called the Le Chatelier principle, and it just basically shows how or explains how a reaction gets back to equilibrium. We'll go over it more when you guys take chemistry full year in a couple of years, but I do want you to be aware that that's a thing. So anyway, that's reactions. It's a fun chapter. We'll hopefully most definitely work a lab in there somewhere. We'll do practice on all, the balancing and that kind of thing. But it's kind of just a continuation of compounds, but now we're starting to put them together. All right.